Hello everybody, my name is Angus Law. I'm a lecturer at the University of Edinburgh, and thank you very much for the invitation to speak to you guys today. I'm sad that I can't be there in person, and you'll have to make do with this video. The title of my talk is an introduction to the fire behaviour of timber. And what I hope to do over the course of the next 25 minutes or so is walk through some of the key behaviours of timber when it comes to thinking about the fire performance. So I want to think a little bit about how timber burns, a little bit about the fire dynamics of a compartment that might be made of timber, and I also want to think about the structural stability of timber and the fundamental properties of timber as a material. Before I do that though, I thought it would be good to have a little bit of a think about the context of timber. And of course there's a huge amount of interest in mass timber engineering at the moment, looking at tall wood buildings, looking at large structures made from mass timber. And there's a lot of drivers for that, so particularly at the moment the environmental drivers seeing timber as a means to solve the climate crisis. And what that means as engineers is that there's a lot of pressure to deliver timber buildings. There's a lot of pressure to make this work. And that goes for all of the disciplines. But in the context of fire safety, it means there's a lot of pressure to make sure that these buildings can be built. And that means, I think, that fire safety engineers are potentially coming under quite a lot of pressure just to make these solutions appear to stack up. And what I wanted to do is unpack that a little bit. Now, there's quite a lot of momentum behind timber buildings at the moment. And in fact, this was a clip from a launch event a couple of weeks ago.
How far have we come? How far have we still to go? I'm interested where we're at from your perspective, and where are the challenges?
I think there are a few main questions we have to address always in every conversation first. How about fire resistance? Okay, that's a long story. Everyone knows now. It's safer to be in a mass wood or in a wooden structure building than being in a steel building, whatever. So I think we have gone a way which is it's on the right way. So the facts are here, science is there, experiences are there.
What you can see from that is the speaker there has quite a nonchalant attitude to fire safety. Wave your hands at it and say, whatever, the science is there. And in a way that represents something of a problem for the fire safety engineer, because if we're going into to design meetings where the attitude of the key stakeholders is whatever, fire safety is solved, then that makes it quite difficult for us to think clearly about the hazards and address those in a systematic way. Now, ultimately, if you're a design engineer, and as I understand it, most of the audience for this conference are fire safety engineers, then what you really need to have is a level of confidence and a level of understanding in order to be able to articulate what the hazards are and explain how those can be addressed in that systematic way. So what I wanted to do is go through thinking just about the fundamental ideas around timber, and I think the other speakers are going to talk more broadly about design methodologies and these kind of things. So one of the first things that people talk about when they are, waving their arms at timber and trying to make the questions about fire safety go away is they start talking about charring. And this is an extract from the Financial Times, which is, I guess, a pretty well-regarded newspaper. And you can see what they're saying here is that, in fact, that is, timber, proves very resistant by charring rather than going up in flame. And so there's this idea that it's something is charring instead of going up in flame. And we can look at that a little bit more, the kind of arguments that are presented in order to kind of make people comfortable with the idea of timber building. So here's another example.
Although it's made out of timber, the timber here is a solid panel. So trying to light the timber here is much like trying to light a log with a match. It's a very hard material to light, so it makes it a much safer material to use.
Now, I work at a university and we have a lab, and lighting a log with a match sounds like a challenge, but we'll come back to that later. The key thing is that there's quite a lot of simplifications here, and some of those are about persuading people that actually there are hazards here that are maybe not what they seem, but there is always a danger of oversimplifying these things. And if we oversimplify, then we can actually give people potentially a false sense of comfort, where in fact they should be engaging with the hazards and thinking about how to mitigate them. So what I want to do is unpack timber as a material. I want to think about what timber is. So if we go and look at some timber, I mean, it looks amazing, it looks very beautiful, but it doesn't tell us a great deal about it. If we look a little bit closer, then what we can see is we can see the structure of the inside of the timber. And you can see, I think the analogy is often made to a set of straws that are sort of stacked, lined up next to one another. And that's where the nutrients and the moisture is transferred through the tree, and it forms the wood itself. So if we look at the composition of that, there's essentially three main parts to it. So the first part is carbohydrates. About 70% of the timber is comprised of carbohydrates. The second part is lignin. About 25% of the timber is comprised of lignin. And then there's sort of a residual trace of minerals there. So if you think about the carbohydrates and the lignin, those are both organic molecules, so they can burn. The minerals are not. They're going to be inert, and they're going to be what's left after the thing has burned. So if we look at carbohydrates, when we think about carbohydrates, one of the first things we, I guess, think about is food and the calories associated with carbohydrates. So of course, if we're making something out of carbohydrates, then that means it's got quite a high calorific value. Lignin is a little bit of a funny one. So lignin is the stuff that if you're going to smoke some food, you want to get the lignin out into the gas phase, and it's what gives your food that tasty kind of smoked flavor. So it's the pyrolysis of lignin that actually leads us to have smoked food. The minerals, well, that's just what we have left behind after everything else has reacted and combusted and gone away. So that's the ash that you would see at the end of a campfire. So those aren't the only things that are going on in timber. We've also got some other materials as well. So we've got water, quite a lot of water in trees, and they're often dried out quite a lot in order for us to use them in the built environment. And then we've got two other things as well. We've got this stuff called resin. So resin is the stuff that Richard Attenborough had his preserved mosquito in, which comes out of a tree and is stored within a tree. And that resin, when it solidifies, you can preserve your mosquitoes in it, but it is dissolved in a liquid, and that liquid is turpentine. And of course, turpentine is very flammable. So there we go. We've got quite a lot of different things going on just within a tree. Some of that is part of the wood structure itself, and some of that is kind of mobile within the tree. And if we look at this in terms of what happens as we heat the timber, what we start to see is if we take a tiny little sample and we heat it from 0 through to say 600-700 degrees, it starts off with 100% of its mass and then it dries out. Once it's dried out, it doesn't do very much for a little while, and then once we get to about 200 Celsius, it starts to degrade. And what we have is a reaction of the material to the heat, and that's the pyrolysis. So we start to get pyrolysis gases leaving the timber. Once all of those have been driven off, we're left just with carbon, and that carbon then continues to oxidize from around 300 Celsius through to kind of 600, something like that. And at the end, of course, all we're left with is that ash. So what I want to do is I want to look at these processes visually. I want to have a look at them as well as looking at a graph of them. And if I were to take a block of timber and I were to expose it to a radiant heat flux, so using a mass loss cone or a cone calorimeter, what we would see is we would start to see those processes. And if I expose it to a relatively low heat flux, then they can happen quite slowly and we can get a nice little look at it. So here we've got a sample of timber being put under a mass loss cone. The heat flux on the surface is 20 kilowatts. So initially not very much happens, but if we speed it up, what we can see is that we have a pyrolysis reaction taking place. So the fuel is being driven off from the surface of the material into the gas phase, and what we have left behind is a char. Now, under 20 kilowatts, that's not enough to ignite the fuel, the pyrolysis coming off by itself. So what I need to do is I need to introduce a pilot. So I can light, if you like, a log with a match if I'm already heating it at around 20 kilowatts. And so what you can see then is we have a flame forming, and that is spreading over the sample and is continuing to burn. Now, if I turn the heater off, what happens is that will just go out. So let's just look at that a little bit more closely. What we've got here at the bottom is the virgin timber. Then what we have is the pyrolysis gases being driven off, and what is left behind is that carbon, is that char. We've also got ash forming on the surface here, and of course when I light it, those pyrolysis vapors, they ignite and they start to burn. And this brings me to the first thing that I wanted to highlight. If we're relying on a char layer to protect our structure, then what we have to recognize is that char is created by pyrolyzing the material. The char is created by releasing flammable vapors. And so what that means is that if we want a char layer, we have to generate fuel, which of course has the potential to be ignited. And if it's in a big compartment fire, then there's always going to be a pilot there to set it off. We're always going to end up burning our timber in order to create the char layer that's going to serve to somehow protect it. So why does this matter? Well, I think some of the other speakers are going to talk about compartment fires and these kind of things, so I'm not going to go into too much depth there because I'm sure they're going to cover it. But if we look at this example, and so this was a test that was run at NIST by Joseph Su and Matt Haler, and thanks to them for giving this photo to me to use. What you end up with, if you have lots of exposed timber in a compartment, is a very big fire. Now, of course, I've not shown you the reference case here, but suffice to say you release a lot more fuel if you have timber linings than if you don't. So you get bigger flames, you get a bigger heat release rate, these kind of things. And of course, there's always the possibility that our timber compartment might not go out. So in one of the cases that were tested at NIST, the compartment just continued to burn until there was some kind of failure, and I guess it was extinguished manually. And so this is a little bit of a concern. By bringing this fuel in and relying on the release of fuel in order to form a char, what we're doing is we're really changing the hazard that we have within a compartment. Now, one of the key questions, of course, is my fire going to go out? Is it just going to keep on burning until someone comes along and sprays some water on it? Or is it actually going to go out by itself, like the example that I just showed you a few minutes ago? And the answer to that will depend on the particular configurations and the fire dynamics within the compartment. So essentially, if there's enough feedback to the timber, well, the timber will continue to burn. If there is not enough feedback, or if it managed to form a thick enough layer of char, then the compartment might start to go out. And of course, this is where we get lots of complications in terms of delamination, because of course, timber is comprised of CLT rather, is comprised of many layers. So we might have delamination, bits of it falling off and then continuing to burn. And we have a lot of complexity in terms of the interaction between the burning timber and the compartment fire dynamics. But as I say, I think some of the other speakers are going to be talking about that a little bit. So what I wanted to do instead is really dig deep on this question of the char itself and what is going on within the timber. So what we've got here is a slice of timber from a sample that was burnt for quite a lot longer than the example that I showed you before. And what we've got is a char layer at the top, virgin timber at the bottom, and this pyrolysis zone in the middle. And the question about how the timber is going to burn is going to be really dominated by the heat transfer to that pyrolysis zone. If there's a lot of heat transfer to that zone, we're going to gas fly a lot of fuel, and that means the timber is going to burn relatively vigorously. If we have very little heat transfer to that zone, then everything's going to slow down a lot, and the timber, I guess, eventually is going to go out. So understanding how the energy is arriving to that pyrolysis zone is absolutely critical in terms of understanding how the timber burns and whether or not it's going to go out. So if we go back to the example that we were looking at before, what we have here is we can see it, we've got the mass loss of the timber. We can see those vapours escaping from the surface. And they're being driven off by an applied heat flux. And the thing that links those two is the heat of pyrolysis. And so we can write that as a simple equation. So we can say that the mass loss rate of the fuel is equal to the net heat flux divided by the heat of pyrolysis. And of course, that's going to be true irrespective of whether or not the thing is on fire. So if I light it, that's still what's going on. But now I've made my problem just a little bit more complicated, because it's not just the applied heat flux to the surface that is going in. I've now got a flame there, which is creating a feedback and is making it quite a lot more complicated. So if we break this down and we look at it, there's quite a few components here. So we've got the heat flux arriving at the surface of the sample that's imposed from somewhere else, in that case, the cone heater. And we've also got losses from the surface. If we have a flame, then we've also got the flame heat feedback. But there's also some other things going on here. We've also got the potential to generate release energy in our char due to the oxidation process. And of course, we've also got the potential to store energy in our char as it gets hot. And finally, of course, we've got the losses of energy out the back of our timber. And so there's quite a lot of things going on here in terms of, well, what is the net heat flux arriving at my pyrolysis layer? It's actually going to be a function of all of these different things. And on the one hand, this makes it look like a horrible equation, but on the other hand, what this allows us to do is think quite rationally about how we might quantify each of these different components and which of them are more important in which situations. So let's have a look at what this looks like if we have an actual sample. So this is some data that was generated by an MSc student called Snorri Arnason, who did his MSc with us here in Edinburgh a couple of years ago. And he ran basically the same experimental setup that I just showed you, a small piece of timber with a heat applied to it. And so what we have, if we expose our sample to a heat flux, we've got an initial peak there where you have a very high mass loss rate. And then as the char layer forms, then that starts to drop off. And so this was some of his data. Now, what Snorri did was he did that a whole bunch of different times. So he did multiple repeats, and he got the same kind of behavior as you would expect each and every time. And so what this means is if we're looking at how timber behaves, there are some aspects of it that are very predictable. And that's something that people like to say about timber. It burns in a predictable way. And we can draw a line that looks something like this all the way through our data, and we can say, yeah, we understand pretty well how the mass loss rate responds as a function of heat flux and as a function of time. The trouble is, though, and you probably noticed, is all those curves stopped in different places. And that's because what we were doing is looking for the extinction. When did the timber go out? And we've got a real range there. The quickest one went out in around 13 minutes. The longest took around 90 minutes. And we have everything in between. So this is kind of problematic because on the one hand, we know pretty well how the timber is behaving. But on the other hand, actually, there's quite a lot of variability in potentially one of the most important parameters, which is the point of auto-extinction. Now, to give you an idea of what this might mean for a piece of timber, the difference in the mass loss between these different samples, so the one that went out really quickly had only lost about 10% of its mass over the duration of the experiment. The one that burnt for 90 minutes had lost about 40% of its mass over the duration of the experiment. Now, if we're thinking about the residual capacity of sections, how much timber is there left in my building in order to, ensure that people can evacuate or to support the operation of the fire service, then losing 40% might be quite a problem compared to only losing 10%. So it really matters to understand when is this timber going to go out. And one of the challenges, although we heard at the start of this talk that the science is done, the science is there, is that, well, we do have a good understanding of some aspects, but translating that into predictions is really very challenging. And I would say we're not there yet, even for a very small piece of timber like we saw in the experiment, let alone a 13-story timber building. So this brings me to the first point that I wanted to really make, I guess, which is we know quite a lot about how timber burns, but there's also a lot that we don't know. And if you're a design engineer working on a project where you're relying on the extinction of the timber, then that should be of concern to you, because you need to understand where our knowledge is good and where our knowledge is confident and where actually we don't really know. Are we actually designing, if you like, in the dark? Now, the next thing that I wanted to touch on today was to think more about the structural capacity of timber. Now, this is an extract from the BBC website. As a Brit, of course, we believe the BBC is an excellent source of very reliable news. What it says here is that in this respect, CLT wins hands down over steel and concrete, which tend to melt and weaken in a fire. And so I wanted just to unpack that a little bit, because as we saw at the start,
it's safer to be in a mass wood or in a wooden structure building than being in a steel building, whatever.
So what I wanted to do was look at this in terms of a comparison between timber and a more traditional material, concrete. So what we've got here is we've got temperature along the x-axis, and we've got the residual strength up the y-axis. And concrete doesn't do very much up to about 100 Celsius, and then it starts to degrade, and then by the time you get to 400 or 500 Celsius, it's degrading very rapidly. And if we look at what happens to a concrete slab, for example, in a fire, what you'll see is that the surface of the concrete pretty much tracks the gas temperature of the fire. So it gets very hot very quickly, and of course has got no residual capacity left. If we look further inside the concrete, what you'll see is that starts to get hot as well, but it takes a little bit longer. And in fact, the concrete can continue to heat quite a long time after the fire has gone out. Now, if we look at timber, the same thing is true. But if we look at the residual capacity of timber as a function of temperature, then actually we get something quite dramatic. So we get a real drop-off at 100 Celsius, and of course by 300 Celsius, the timber is just not there anymore. We just have char left. Now, this starts to matter when we start to look at large elements of timber and how they're used. And so this was a little piece of research that was done by a colleague of mine, Felix Weisner. And so what he did was he took some data that had been generated for a real project in Norway. And what had happened was the design engineers had taken their timber columns, that were huge, and put them in a furnace, subjected them to a 90-minute fire, taken them out of the furnace, they'd gone out, and they continued to monitor the temperatures. And what they did was they calculated, well, what was the crushing capacity of that structural element be as a function of time? And what they found is that after the 90 minutes, they still had around 50% of the capacity of the column left, which is typically enough to bear the fire limit state loads. Now, what Felix Weisner did was he took that same data and he just continued to make the calculation after the 90 minutes. And of course, what he found was that the temperature inside the element continued to rise. And what that meant is that the structural element continued to lose strength. And what he found was after about 270 minutes, there was only 13% capacity left within these structural elements. So if you're working on a project that's relying on the structural elements to support, for example, firefighting operations, you might want to think quite carefully about whether or not you believe they're at risk even after they've put the fire out. Similarly, you might want to think about if you're designing a building that has a stay put or a defend in place strategy, is it okay to leave people in that building even after the fire has gone out if the structural capacity is going to continue to degrade? So that pretty much brings me to my second and final point, which is that timber is weak at warm temperatures, and we need to be really careful with that until we've understood what that means for our structures. So that's pretty much everything that I wanted to say. I guess the last thing is just to say if you are working on one of these buildings, then just take care that you're not getting pushed into doing something that you're not entirely comfortable with, or that is starting to violate the assumptions of the methods that you're working with. Similarly, don't get pushed into doing something that isn't yet supported by the science, because you're taking a real risk with that in terms of both what you're doing and also potentially the people occupying the building. And last but not least, please don't just wave your hands and say, whatever. Think about the hazards and try and address them systematically. Thanks very much for listening, and look forward to taking questions.